Welcome to this explainer. Today, we're diving straight into one of the most fundamental mysteries of thermodynamics. Have you ever wondered why some chemical reactions just happen entirely on their own? And more importantly, how on earth can we mathematically predict them? Here's our roadmap for today. We'll start with spontaneous change, then move into entropy and disorder. After that, we'll look at the surroundings, dive into Gibbs free energy, and finally wrap up with temperature effects. All right, section 1, spontaneous change. What exactly drives it? So why do some physical or chemical changes happen completely on their own, while others just, well, don't? Think about spilling a few drops of perfume in a closed room. You know how the smell gradually spreads everywhere totally on its own? Or think about giving a single spark to methane gas. It ignites and just keeps burning. These are what we call spontaneous changes. Once they get started, they carry on naturally without you needing to constantly pump energy into them. But what's actually driving that behind the scenes? Imagine a setup where we've got helium and argon atoms chilling in separate gas jars. When you open the valve between them, the gas atoms just spontaneously diffuse. They mix. Why? Because of the pure laws of chance and probability. There are simply, mathematically speaking, exponentially more ways for the atoms to be mixed together than to stay perfectly separated in their own little flasks. It's basically a game of microscopic statistics, and the messy, mixed-up state, it's heavily favored to win. Moving on to section 2, entropy and disorder, measuring the mess. Okay, so the absolutely crucial point here is understanding what entropy actually is. Entropy, which we represent with the letter S, is a measure of the dispersal of energy at a specific temperature. To make that a bit easier to visualize, just think of it as a measure of the randomness or the disorder of a system. Get this, a chemical system actually becomes energetically more stable when it gets more disordered. It turns out the universe literally loves a mess. Think about the sheer contrast of disorder here. On one hand, you've got a highly ordered, perfect diamond crystal. Because its carbon atoms are rigidly locked into a regular lattice, it has a very, very low entropy value. Now compare that to a liquid like bromine that is turning into a vapor and spreading all over. That vapor has super high entropy. Why? Because its particles are spread way far apart, they're moving randomly, and they're taking up vastly more possible arrangements. When we visualize this change, watch what happens to the entropy of a substance as we steadily crank up the temperature. As a solid melts into a liquid, and then especially as it boils into a gas, boom, you see these massive upward jumps in entropy. And it makes total sense, right? The disorder of the particles drastically increases when they break free from their rigid bonds. They stop just vibrating in place and suddenly start translating, rotating, and moving completely freely. When looking at standard molar entropy values, a really clear trend emerges. First off, simpler substances generally have lower values than complex ones with lots of atoms. But more importantly, consider the physical states. Gases, like carbon dioxide gas with a value of 213.6, generally have much higher entropy values than liquids, and they're definitely way higher than solids, like solid calcium, which is sitting way down at 41.4. So the physical state of matter is a massive indicator of just how much disorder is going on. That brings us to section 3, the surroundings beyond the system. To really grasp spontaneity, we have to clearly separate the system we're investigating from the surroundings. The system is just the chemical reaction itself, the exact reactants turning into products. The surroundings? Well, that's literally everything else. The water acting as a solvent, the air around the test tube, even the glass of the test tube itself. You see, a spontaneous reaction isn't just about the system getting messier. It's entirely dictated by the total combined entropy change of both the system and the surroundings together. So how exactly do we find this total entropy change? It's a pretty straightforward 3-step mathematical process. Step 1, we calculate the system's entropy change. You just subtract the sum of the reactant's standard entropy from the sum of the products. Easy enough. Step 2, we calculate the surroundings entropy. We do this by taking the negative enthalpy change of the reaction, that's negative delta H, and dividing it by the temperature in Kelvin. Finally, step 3, just add those two values together and bam, you've got your total entropy. Now, think about how this applies in the real world. Take an exothermic reaction, for example. Because it releases energy in the form of heat, that heat goes directly out into the surroundings. And what does that do? It increases the random movement, rotation, and translation of the molecules in the air or the solvent around the reaction. This massively bumps up the entropy of the surroundings. All this extra disorder makes the total entropy much more likely to be positive, which in turn makes the reaction much more likely to happen spontaneously. All right, section 4, Gibbs
free energy, the master key.
Meet the American scientist Josiah Willard Gibbs. He took these really complex concepts of entropy and energy and applied them to physical processes and chemical reactions. Before Gibbs came along, figuring out if a reaction would happen was honestly pretty tedious. You constantly had to calculate the surroundings' entropy using the reaction's heat output. But Gibbs, he gave chemists a straightforward way to predict feasibility using a brand new quantity, free energy. This meant we wouldn't have to manually calculate the surroundings every single time, a real game changer.
Let's quickly walk through Gibbs' incredibly elegant derivation. He started with our total entropy equation from earlier. Delta S total equals delta S of the system minus delta H over T. Next, he multiplied the whole equation by negative T just to clear out the fraction. Finally, he substituted that chunky left side, negative T times delta S total, with a single clean new symbol, delta G. And that leaves us with the famously elegant Gibbs equation. Delta G equals the change in enthalpy minus temperature times the change in system entropy.
Okay, so the absolute golden rule to lock into your memory here is this. We already know that for a reaction to be spontaneous, the total entropy change has to be positive, right? Well, because Gibbs multiplied by a negative temperature to derive his equation, the sign actually flips. Therefore, its mathematical counterpart, delta G, must always end up as a negative value for the reaction to proceed on its own. It's that simple. If delta G is negative, the reaction is spontaneous. If it's positive, no way, it's not going to happen.
And finally, Section 5, temperature effects, the ultimate tiebreaker.
Let's look at the extremes where things are super clear-cut. When enthalpy and entropy actually agree, predicting spontaneity is a breeze. Look at case 1, an exothermic reaction giving off heat that also creates more disorder. Both factors want this reaction to happen. So this reaction is always spontaneous no matter the temperature. But case 2 is the exact opposite, an endothermic reaction that absorbs heat and decreases disorder. Here, both factors are fighting spontaneity. Delta G will always be positive, meaning this reaction will absolutely never happen on its own under any conditions.
But what happens when we have opposing forces? What if an endothermic reaction creates more disorder? Enthalpy is saying no, but entropy is screaming yes. Well, just look at how the math plays out. At low temperatures, it won't work. But at high temperatures, that T times delta S term in the Gibbs equation becomes mathematically massive. It grows big enough to completely overpower the positive enthalpy. When that happens, it turns the overall delta G negative, sparking a spontaneous reaction. So temperature literally acts as a switch, flipping the reaction from non-spontaneous to spontaneous. So as you look at the physical world changing on its own around you, the next time you see ice melting on a warm summer day or metal slowly rusting on an old car, ask yourself, which invisible force, enthalpy or entropy, is winning the thermodynamic tug-of-war right now? It's amazing to consider the incredible mathematical balance of Gibbs-free energy that is secretly driving every single reaction in the universe. Thanks for joining me on this explainer, and keep questioning the spontaneous world around you.